let me remind you, what is the pepper problem? And then I'll give you the 3 solutions, and you guys pick which one you like the best. I'm trying to show you that there's lots of different ways to do these problems, and depending on what you feel like, one might be better or the other, or it could sometimes just come down to personal preference. But the pepper problem is you have the tiles P, E, P, P. You have 3 P's in your hand. E, R. So you've got 6 of these Scrabble tiles, and you shake them up, and you take them out one by one. What is the probability it spells pepper? So the probability it spells pepper. So you're taking them out and putting them out in order. And we saw last time, I think the chance is 6. Yeah. Nope, 12. Okay, 12 out of 720, also known as 1 out of 60. And depending on how you do it, you might come out with 12 out of 720. You might come out with 1 out of 60. Of course, they're both the same number, but depending on how you think about it, you'll get one or the other. So that's the problem. And that was the answer. I'm about to do the solutions. Are there any questions about what the problem is before we do it? Does everyone remember the problem from last time? Okay, so here is my first solution. I broke down the solutions. I said you either are going to use unordered things. Unordered. This is like the unordered way. And in the unordered way, I only ever use these choose things. So there's going to be these choose things floating around. There's going to be like 6 choose 2. There's going to be like 6 choose 3. These things. So using things like this. Okay, so here's the first way. And this is a little bit of a trick that we haven't seen yet before, which is I'm going to take the numbers 1, 2, 3, 4, 5, 6, and think of, when you write out the word pepper, you are thinking about putting the tiles out in order. But there's another totally equivalent way to think about it. If you take pepper and you label the slots here. So this is slot number 1, and slot number 2, and slot number 3, and slot number 4, slot number 5, and slot number 6. The word pepper is actually ways to arrange slots 1, 2, 3, 4, 5, 6 with the letters 3 P's, 2 E's, and 1 R. So you can think of, here's P. I'm going to put 3 slots in here, maybe 1, 3, and 4. Here's E. That's going to get 2 slots. It's going to get 2 and 5. And here is R. And R gets 6. So I've got the slots numbers 1, 2, 3, 4, 5, 6. And 3 of them are going to be P's because there's 3 letters. So the 3 P's have to be somewhere. So they're going to get 3 of these numbers. These slots 1, 2, 3, 4, 5, 6 are going to be in the P circle. 2 of them are going to be in the E circle. And 1 of them is going to be in the R circle. And if I have slots 1, 3, and 4 in the P circle, E's has 2 and 5, and R has 6. That is exactly pepper. If you did it wrong, like if you had, I don't know, 1, 2, 3, 4, 5, and 6, that is the word p-p-p, e-e, or p-p-p-ear, I guess, okay? So that's not pepper. So the slots can be thought of as being put into circles of which letter you have, rather than thinking of the tiles as going in the slots. So it's kind of just a completely equivalent way, but thinking about it on its head. Any questions or comments about how I'm thinking about this? Yeah?
Can you just repeat what that thing means with the brackets and the number?
Yes, okay. Well, that will when I come to that, I'll say it again. Yes. So we're going to use these. I haven't used them yet. So far, all I've done is think about it this way. And then when I get to these numbers, I'll make sure to say what they are. The reason these numbers are going to come up is these numbers count unordered things. And you see that 1, 3, and 4 here are unordered, right? 1, 3, 4 in the P's is the same as 4, 1, 3 in the P's, right? The slots that the P's take up, there is no order. That's why they're going to come up. Yeah, so I'll remind you guys what these are when we get to them. But questions about this weird way of thinking about the problem? Okay. So how are we going to take our 6 slots and distribute them into these 3 bins? The bin of 3 P's, the bin of 2 E's, and the bin of 1 R. The first thing I'm going to do is choose. I'm going to do it in 2 steps. So first I'm going to choose 3 slots to go, and I could even be more specific. 3 slots out of 6 to go into P group. So what I could do is I'm taking these 6 slots, I'm distributing them however I want. I'm going to fill up the P's first. And how many ways are there to do this? This is where it's 6 choose 3. 6 choose 3 ways. And so 6 choose 3 is the number of ways when you have 6 things to pick an unordered group of 3 of them. So this is the total on top here. The total things. And this is the number in the unordered group. Number in unordered group. And so we did the last example we did was with a hand of cards where the order doesn't matter. So we had ace, king, queen is the same as king, queen, ace. If you have a hand with three cards, it's going to be something choose 3. Okay. The formula is 6 times 5 times 4 divided by 3 times 2 times 1. So it's the falling factorial on the top, and it's the regular factorial on the bottom. In this case, 6 times 5 times 4 divided by 3 times 2 times 1. Let me say, sometimes people add in another term, right? They say times 3 times 2 times 1, and then they also multiply by 3 times 2 times 1 over here. Those cancel out, so you're left with what I said originally. And in this case, that simplifies down to 20. So there's 20 ways of these 6 slots to decide where the 3 P's go. So you can think of this as like, I'm deciding where the 3 P's are going to go, and there's 20 ways to do it. 6 choices for the first one, then times 5 times 4, but then we're overcounting by this factor of 6 because you can move them all amongst each other. So 20 ways. That's filling up the P's. That was step 1. Step 1. All right, let's call it step P. That's a good name. Step P. Questions or comments about the step P, filling in the P's? So there's 20 ways to do that. Next up, we got 3 left, right? So of these little bag of 1, 2, 3, 4, 5, 6 slots, I have used 3 of them and put them in the P section. And the next thing I got to do, I got to fill up the E's. So I'm going to choose 2 slots out of 3 to go into the E group. Right? So the E's need 2 slots because there's 2 E's. So which ones are they going to get? Well, we don't know, but how many ways are there? Well, there's 3 slots. 2 of them are going to be E's, so it's 3 choose 2. 3 choose 2 ways. 3 choose 2, by the way, equals 3 times 2 divided by 2 times 1 is 3. So there's 3 ways to choose where the E's go. Once the P's are down, there's only 3 ways left to choose where the E's go. Step E. Okay, and last but not least, step R, put down the R's. There's only one way. Put it in the last place. Last slot. In. One way. Okay. So for example, in the first step, maybe I chose 1, 3, and 4. Out of the 20 possibilities, you can choose 3 things. If you choose 1, 3, and 4, let's get the P's. With 1, 3, and 4 gone, what slots are left? There's 2, 5, and 6. With 2, 5, and 6, one of the ways is to put the 2 and the 5 in the E group. And then you're left with the 6 that goes in the R. That's one way to make pepper. And in fact, this is the only way to make pepper. So this tells me the number of possibilities, total ways. The total ways, you just multiply everything. So you can imagine this like a probability tree where at step P there's 20 branches, and then step E there's 3 branches coming out of that. There's 20 times 3 times 20 times 3 times 1 total ways. That's 60. So there's 60 possible sort of words you could get if you think of each word as being unordered. Last but not least, what's the probability? The probability of get pepper. It's just going to be 1 because there's only one way to make pepper as an unordered set. Only one way to make pepper, right? As unordered things, the only way is the way I showed you over here. It's you got to have 1, 3, 4, you got to have 2, 5, and you got to have 6 because we're thinking of these as unordered. 1, 3, 4 is the same as 4, 1, 3. As long as you have those 3 things in your P bag, then you're good. Okay, 1, and then the total number of ways is 60. That's what we just found. Total, and that's the answer. So this is if you like putting a 1 on top, this is how you would do it. The hard part is finding the total on the bottom. This is how people like to do it on the internet. If you Google on the internet, this is the most common solution. I think this solution is pretty tricky. I think the other ones are a little easier, but some people like this stuff. And if you get good at it, you can get quite quick at these things. So maybe I'll leave it at that. Sometimes this 60 is called a. Some people say 60 is 6 choose 3 comma 2, and then you kind of like speed this thing up. But this is more complicated than we need to be. So you might see this online, or 3 comma 2 comma 1 might see online. Some people call this a multinomial coefficient, but I'm not one of those people. Okay. Any questions or comments about this solution? Yeah.
For the 6 choose 3 and 3 choose 2.
Yeah.
Is that the same thing as putting like 6 3 in our calculator?
No, because it's a combination and not a permutation. So it might be the same as putting the combination button. I don't recommend doing it on your calculator for the following reason. When students have a calculator, they will type things on the calculator, and if they make a mistake, they don't notice. You should just do it like this and calculate. Look, 3 times 2 cancels with the 6, and you get 5 times 4. I've seen students answer questions like this, and I don't know what they do wrong, and they put in like 40 billion over here, because they did something weird on their calculator, and it comes out to like 40,300,577, and then they just write that down, and they lose the mark. It's very sad, because they could have just done it, like a regular person. So yeah, maybe you can do it on your calculator, I don't know. But you don't need to, I don't know. Also, if the question just says, give me the answer, this would be perfectly fine. Other questions? Yeah.
For step E, you went 6 times 5 times 4.
Yeah.
Step E, you went 3 times 2, and then under that you also have 2 times 1.
Yeah.
On top of 3 times 2 times 1, so the 4 of step E.
Yeah, why are there 3 things over here, but only 2 things over here, right? Is that the question?
I understand why there's 3 and 2, right? I don't understand why it goes 6, 5, 4, and then over 3, 2, 1. But on the other one, it goes 3 times 2, and then over 2.
Yeah, so the rule is, and we did this one last class, the rule is if you have n choose k, so if whatever number n is on top, then you do n falling factorial with k terms on top and k factorial on the bottom. So you always start at the big number on top, and the number of terms in your falling factorial is the small number. So for example, here I started at 6, and there were 3 terms, 6, 5, 4. On the bottom is always the bottom number factorial, so you start at that number and go down. So 3, 2, 1. Over here, it was a 2. So I start at 3, and I go 2 terms, 3, 2. And on the bottom is 2 times 1, 2 factorial. Some people, like I said, memorize this the other way, which is n factorial over k factorial, n minus k factorial. And then you have like a whole other thing to worry about. That's what happens over here. If you actually want to calculate this, there's no reason to do this. They always cancel out, so there's no reason to put them on. Yeah?
For step E there, could you not cancel out the times 2 on the numerator and denominator?
Yes, that's how I got 3. And in fact, 3 choose 2 is like you have 3 things, you got to pick 2 of them. It's a fact that 3 choose 2 equals 3 choose 1. So you could have done that. Choosing 2 things out of 3 is the same as choosing 1 thing out of 3. That would be the same as doing step R first. You could have said, before we do step E, let's pick which of those 3 things is going to go in R. That would be totally valid. It's exactly the same answer. Great question. Anyone else? Yeah.
I don't know for the last step, when you get to the very end, could you just simply just go 6 factorial over 3 factorial times 2 factorial times 1 factorial? You can set it to 1 over.
Yeah, so if that's what this formula is, 6 factorial over 3 factorial times 2 factorial times 1 factorial, and that is the right answer. And if you calculate everything we did, that's like what you'll see, that's what we got.
Yeah, so what I had to show word above it, just do
So if the question says, give me the answer, and you write this down, you got the right answer. If the question says, explain to me why you got the correct answer, and you write this down, then you will not get the mark for showing me why. So showing me why, you gotta do some kind of explanation like this with the number of ways. And I mean, it's true, like that is the answer, and this is why, so like you're gonna get that answer. Okay. Other questions? These are very good. Okay, so we got 1 out of 60 this way. The other way that you can do it is as ordered tiles. This one's a bit quicker if you ask me, ordered tiles. So as ordered tiles, what you have to do is take Pepper and imagine that the tiles are actually secretly in order. So there's P1, P2, and P3, and E1 and E2, and there's just one R. So R is just R. But imagine you can actually keep track of the different P's. And if you do it this way, there's more than one way to get the word pepper. Because, for example, you could do this. P3, E, let's leave the E. So you gotta spell pepper. Now if you think of them as ordered, there is multiple ways to get it. So here's another way you can get pepper. So if you think of the tiles as being distinguishable as ordered tiles, so the order matters, then there's multiple ways to get pepper. And how many ways are there to get pepper? How many? Ways? Well, I claim there's 3 factorial ways to mix up the P's. So there's 3 P's, P1, P2, and P3. You can put them in any order. That's a 3 factorial, right? 3 choices for the first, 2 choices for the next one, 1 choice after. And there's 2 factorial ways to mix up the E's. So same idea. There's 2 tiles. You can put them in any order. That's 2 factorial. So if you're thinking of them as ordered, you often use n factorials used. So unlike the last one was all choosing, this one is all putting things in order with n factorials. So there's 3 factorial ways for the P's, 2 factorial ways for the E's. You can do any mix and match of any of those. So the total number of peppers, number of ways to make peppers, number of pepper is the product, 3 factorial times 2 factorial, also known as 12. 3 times 2 times another 2. Okay, so there's 12 different ways to make pepper. Now you gotta ask, how many total combinations are there? And now there's 6 tiles, so the total number of ways is 6 factorial. Total arrangements is 6 factorial. And again, that's because there are 6 tiles, and a factorial counts the number of ways you can put them in any order, the full tree. So 6 factorial is 6 factorial. That is 720. So the final answer this way, the probability of getting pepper in this way of doing it is the 12 ways to get pepper divided by the 720 total ways. And you see that works out to exactly the same thing as 1 out of 60. It's the same answer, it's the same problem. We're just doing it a different way, and we're thinking of grouping things or not between this one and the last one. And once again, yeah, the answer, you can write it as 3 factorial times 2 factorial divided by 6 factorial is kind of exactly 1 over what we had before. All right. Questions or comments about this way of doing it? Yeah. How do you show that 3 factorial is equal to what? Okay, this is, why are there 3 factorial ways to mix up the P's? So the definition of the factorial was when you have n things, the number of ways to mix them up fully is n factorial. And that really came from the tree, so we kind of derived this last time by a tree that looked like this. I guess it was 2 classes ago now. So, right? So the first choice, second choice, and third choice. So when we first did it, I went into a lot of detail of where does the factorial come from. In fact, we solved this problem before we gave it a name, right? So we solved this problem. We said there's 6 ways. We thought about the 3 choices for the first one, 2 choices for the next one, 1 choice for the last one. And then at the end, we gave it a name. We said that's 3 factorial. And now we're kind of like using that as its own little idea, right? So every time we come across 3 things, we don't have to draw the full tree. We just say, oh, that's a factorial. We gave that a name 2 classes ago, and we use that. So this is how you build up to really hard math problems, is you take what used to be a hard math problem, you give that a name, factorial, and then you use it to work up to harder problems. Yeah. So yeah, if you need a refresher, you might need to go back and see what the factorial was from 2 classes ago. All right, other questions or comments? Okay, last but not least, the very short way to do it is the pure probability tree. And this is the one that we were drawing when we did the birthday problem. To get pepper, you need 6 things to go your way, all in a row. So you're drawing these tiles out of the bag, and you need them to all work out perfectly. So the first tile better be a P. The second tile better be an E. The third tile better be a P. The fourth tile better be a P, and then an E, and then an R. So in other words, to get the word pepper, you can think of it sequentially. First you need a P, then you need an E, then you need a P, and so on. The probability of the first P, this one has a chance 3 out of 6. That's because there's 3 P's in the bag, and you're pulling one out at random. So you have a 3 out of 6 chance of getting what you need, and then you have a 3 out of 6 chance to fail immediately. You fail. So with a 3 out of 6 chance, your first letter is wrong, and then it doesn't matter what happens after that. You're not spelling pepper. If the first letter you got was an R, there's no way. Given that you got a P, now there's 5 tiles left in the bag, and you can ask, what's the probability of getting the next thing? This is like an urn problem, right? Conditionally, the probability of getting an E given that the previous step was a P. So really, this is P given P first. So this is just like a problem we did before. I claim there's 5 tiles left in the bag. There's 2 E's, so this one has a 2 out of 5 chance. Similarly, for the next one, what's the probability of a P given you had the first P and the second E? Like, given that you had everything before. Well, now there's 4 things left in the bag. How many of them are P's? Well, 2 of them are P's. The next P, there's only 1 P left and 3 tiles, so that's a third. The last E, there's 1 E left and 2 tiles in the bag. And once you've gotten to P, E, P, P, E, you're definitely good, because the last tile in the bag is definitely an R. This one has a 1 out of 1 chance to be what you want. So, again, I did this quite quickly because we did a lot of time on it for the birthday problem and for cards. This is this idea of a probability tree where you need a bunch of things in a row, and if any of them goes wrong, then you are off the path and the event didn't happen. So that's like a probability tree that's like very narrow. How do you find the probability? You multiply all these conditional probabilities together. So the probability of you get pepper, it's exactly 3 out of 6 times 2 out of 5 times 2 out of 4 times 1 out of 3 times 1 out of 2 times 1 out of 1. So a little bit annoying to write down, but you'll notice that it's actually 6 factorial on the bottom and 3 factorial times 2 factorial on the top. It's the same answer, 12 out of 720. Okay, so that's the last sort of way to do it that gels with what we were doing a few classes ago too. Questions about that one? Okay, now the $1 million question. Which of these 3 methods do you like better? Let's answer sort of quickly. So the code is YAQU. I never wrote it. You tell me which one you like. I'll just give you 1 minute. So don't belabor which one you like too much. Go in there and let us know.
Mihai,
Yes.
query for you.
Ah, okay, yeah. Okay, let me write the code and then I'll come yeah. All right. I have to press open. Okay, great. Okay, it's open. Now do the thing. Yeah, so that's similar to the last one. Yeah. So I think what you should be able to do is draw the probability tree. It gets more complicated. Like what, there's a rule where you draw a key that like the letter E lights on fire or something, then you'll still be able to do it with a tree. Whereas like this really is a straightforward tree where you too specific. The probability tree you can add in any kind of tree. So you should be able to translate this into a tree.
It's useful for the next one.
That was the first one, yes.
Yeah, I don't use it that much. I use it, I maybe 2 questions a day.
Okay, it's been a minute. I'm going to stop the thing. I know I normally put up a timer, but I'm not doing a timer because it's just, how do you feel? You'll also notice this is an important life lesson. When you have 3 options and you want to know what somebody's favorite is, don't make them choose one, because then you might split the vote. Maybe like most people like these 2, but it splits, and then this one comes out ahead. So I said you can pick all that apply. That's called approval voting. That's better. Okay. What did people approve of? What ways do people like to do it? Okay. And we see that probability tree is the most common. That's what we taught you a while ago. I like the probability tree as well. The reason really to learn these things is when the problems get really, really hard, like even more complicated, then knowing this kind of stuff is even, more helpful. And indeed, yeah, the internet loves this way to do it, but I think it's the hardest way by a fair margin. So the factorials, I think, is also quite nice, which most people, not too far ahead. Okay, I think we're going to stop there and go on to something completely different. Okay.
On to something different. Okay, don't want that. Don't want that. Don't want that. Where am I? Okay. Okay, here's what I want to do. In a moment. Just a sec. We just lose everything? PowerPoint not responding.
You're on the HTML.
Okay, get me internet.
The back of your... Oh, okay. Do you need the internet?
It's because PowerPoint likes to check your license these days.
Oh, I see. Okay.
Absolutely a pain in the ass.
Well, it is blinking, so sometimes it gets your background and sometimes it doesn't.
Okay, let's just hang on. What the hell is he doing? Not responding, not responding, not
Could it
responding.
be something as simple as it's really now you have nothing. Oh, okay, there we go.
Think it's going?
So it's going, yeah, you have like a new window, I guess.
Let's go. Function F7 is probably screwed up.
Oh, I see. Can you tell PowerPoint to cool it?
I can try. Is it up there? It's up there.
It's up there, yeah.
It's up there.
Well, here we could freeze it, and then you would at least have it.
Just that.
It's true, you're still not connected to the internet.
Absolute pain in the butt, but nonetheless.
Yeah, you're planning to work on the
Yeah, I'm gonna work on these, and that'll eat up the class anyhow.
Here, we could freeze
Just
one of them
freeze that.
so that it.
Just
you want it
freeze
frozen
that.
on both?
Yeah,
you
freeze
want-
it.
Well, you want the
gotta
dot
go to
cam
dot
on.
cam
Okay.
over here.
So there you go. Okay.
Dot cam over here. Okay. Okay. So what's happening? I'm having a technological glitch where the PowerPoint's not responding. However, what we are working on today really just gets back to this question that I dropped off on you somewhere between September 16th and 20th. It's in that set of slides. Okay, and hopefully you went and gave these a try, but because a couple of these problems are not that easy. But they were following up on an urn problem we worked with previously, and I'm going to quickly lay out the tree we worked on. But first of all, we're going to ask ourselves, what are these questions that are being asked to us? And so we had our urn. We had 3 reds, we had 2 whites. Okay, and we picked 2, either without replacement or with replacement. The interesting question for most of these is without replacement. A couple of them are trivial for with replacement. Not all are trivial without replacement. And the first question asked, what is the probability at least one ball is red? And so we defined also R1, first ball drawn is red. And R2 is the second ball drawn is red. Or we might refer to Ri is the ith ball drawn is red, and where I equals 1 to 2. This is a little more general way of labeling up our notation, in the sense that we can now talk about any number of balls being drawn. Okay, so let's go through and ask ourselves, first of all, what questions are we asking? So the first question says, what is the probability at least one ball is drawn? And so our first question, I'll just call it number 1, is we are looking for the probability that the first ball drawn is red or the second ball drawn is red. The second question says to us, what's the probability the first ball drawn was red if the second ball drawn was red? Okay, so that is asking the probability of getting a red on the first, given I got a red on the second. Okay, that's not as simple as it might appear. The third question says, what is the probability the second ball drawn was red if we don't know the color of the first ball? Okay, so that's the probability the second ball drawn is red, and I know nothing about the first ball, so there's nothing conditionally that I know. And if it is known that at least one ball drawn is red, what is the probability that both balls drawn are red? Okay, so again, thinking that in terms of notation, it's known that at least one ball drawn is red. Well, that was R1 union R2. So I've got the condition that we know that at least one ball drawn is red. And then we ask the question, what is the probability that both balls are red? And so that's R1 intersect R2. Okay, so we've set up what our questions are here. And they're going to be the same questions whether we do it without or with replacement, but we are going to do, we're going to go through the without replacement ones. And there's a couple things to watch for as I go through this. And so at this point, I'm going to actually switch this one over to the dot camera over there, I think. And I'm just going to freeze that one so you can kind of remember what we were working with. So we've got everything we need. We don't need the slide anymore. Okay. So let's quickly lay out our tree again. And the tree will just make it a little easier to think about why I do what I want to do. And so we got our first pull, and we could either get a red on the first or don't get a red on the first. In other words, you get a white. Okay, and that probability was 3 out of 5 for getting a red on the first. There was 5 balls. We don't need to go through that again, and that's 2/5. And then on our second pull, our probability of getting a red on the second was dependent on what happened in the first poll. So if we got a red on the first, the probability of getting a red on the second, that was 2 out of 4. There's only 2 red balls left and only 4 balls left, so that was the probability of R2 given R1. And the probability of not getting red on the first, in other words a white, was 2 out of 4, which was the probability of not R2. I'll use a little c. Excuse me, I'm a junkie on primes. I like primes rather than these little c's, but we're trying to stick with little c's as much as possible. Okay, we got that. And so, of course, if we didn't get a red on the first, in other words, we got a white, again, I could either got a red on the second or I didn't get a red on the second.
Gary, you're just off the bottom.
Oh, I'm off the screen.
There you
Yep, let's keep it on the screen. So, if I got a white on the first, I'm still got all 3 whites, or all 3 reds left, so that's 3 out of 4 is the probability of a red on the second, given I didn't get a red on the first. Oh, let me use little c's, little c's, little c's, little c's. Okay. That, and this is the probability. Let's stick with the little c. And I will do this repeatedly, so just kind of get used to flipping this in your mind. So this is the probability of not getting a red on the second, given you didn't get a red on the first. Okay, so we did that, and then we went through and we got all of the intersections. And because I've got multiple colors of markers and they're fun to use, I'm just going to work out these intersection probabilities. And I could go through and write out all the notation. Actually, I'll just go back and just emphasize that this was the probability of a red on the first, and this was the probability of not getting a red on the first. Okay, so we've got all our probabilities labeled on our tree, and we got our intersections by multiplying along the branches of the tree. So for example, the probability of R1 intersect R2 was 3/5 times 2/4, which turned out to be 6 out of 20. And I could either do that or I could reduce it. Well, I can reduce it to 3/10. Okay? And then similarly, you get the probability of R1 intersect not R2, and you take the probability of R1 times the probability of R2 complement given R1, and so you're going to take 3/5 times 2/4 is 6 out of 20, and I'm just going to say it's 3 out of 10. And then coming across here, I've got the probability of not getting a red on the first intersected with getting a red on the second, and that is going to be 2/5 times 3/4 is 6 out of 20, so that's going to come out to 3 out of 10. And the probability of not getting a red on the first and not getting a red on the second, in other words, you got 2 whites in a row, is going to be 2/5 times, I didn't write that number in, oops, sorry, back here, 1/4, that's 1/4, okay, up there, 1/4. So 2/5 times 1/4 is 2 out of 20, which is 1 out of 10. And of course, the key thing to note is you could draw a Venn diagram with these of what happened on the first pole and what happened on the second pole. And you've got 4 intersections, and those 4 intersections are both mutually exclusive and exhaustive That represents our entire sample space, all the possible outcomes for the experiment. Now, why did we beat all that to death? Why did we go over again? Well, we want to make sure that we understand what we're looking for when we ask for the probability of R1 union R2. And so if we want R1 union R2, what have we got? Does this satisfy it? Yes, that satisfies it. That satisfies it. But here we have at least one red. And here we have at least one red. So one solution there is to simply add up those three intersections. The probabilities of the intersections, 3/10 plus 3/10 plus 3/10. The answer is 9/10. Another way you could have gone about doing this question, which becomes really useful if you had several draws, is to say, well, I will have at least one red as long as I didn't miss red every time. And so you could have said, okay, I'm just going to take 1 minus 1/10 because there was only one way I don't end up with at least one red. Okay, so there's a couple of solutions there for you. Now, the second question is, what's the probability of a red on the first given I got a red on the second? Well, didn't we get that for us before? No, we didn't get that answer for us before. What we got was the probability of getting a red on the second given I got a red on the first. That's not the same as the probability of getting a red on the first given a red on the second. How am I going to do that? My goodness. And I can't draw the red on the first after I draw the red on the second, so I have to think this out. And then this brings up a very important, I'll call it a trick. It's not really a trick, it's a solution for attacking this. So I'm gonna do this for the moment. That. Yes, we got that. Okay. So I want the probability of a red on the first, given I got a red on the second. Okay, that's just like a probability of A given B. You take the intersection of those two, the probability of R1 intersect R2, over the probability of R2. Now, how am I going to get the probability of R2? Well, how are we going to get the probability of R2? Interesting question. Interesting question. Actually, that was the third question that we had there, is are we going to get the probability of R2? Okay, so what do we know about getting the probability of R2? What do we know about getting the probability of R2? We know the probability of getting a red on the second, if we got a red on the first, was 2 out of 4. The probability of getting a red on the second, if I got a red on the first, or I didn't get a red on the first, was 3 out of 4. But what's the probability of getting a red on the second if I know nothing about what I got a red on the first? Now, do we have time to slip a mathematized question in there?
I'm not sure we do.
Don't do it. Okay, we had a mathematized question set, but we don't maybe have room to do this. Okay, well, let's consider here that there were 2 ways of getting a red on the second. You could have got a red on the second this way. Actually, let's use a red pen now. We could have got this way to get a red on the second, or we could have got a red on the second this way. Couldn't do it this way, couldn't do it that way. I could do it one of those 2 ways. So, the probability of a red on the second is equal to the probability of a red on the first and a red on the second, plus the probability of getting a red, well, not a red, a white on the first and a red on the second. In other words, if you get a red on the second, you either got a red on the first or you didn't get a red on the first. So that is going to be 3 out of 10 plus 3 out of 10 is 6 out of 10, which is 3 out of 5, which isn't just a coincidence that that is in fact equal to the probability of a red on the first. It is not a coincidence. When we don't have the information about whether we got a red on the first or not, it counts as just drawing a ball from an urn with all 5 balls in there. Now, I'm going to end this right now just saying, given that you've got this, can you solve this question here? And that's what we'll start off with on Friday.